This is part 2 of the 6.01 stoichiometry and its uses lesson. Coefficients and subscripts are always whole numbers in chemical reactions. So, in other words, what we're going to talk about on this slide is the fact that you cannot have half of an atom. The only time atoms break in half is when you have a nuclear reaction, such as fission, which happens in radioactive decay, and also nuclear bombs. In other words, you cannot make it happen. I cannot make it happen. Keep in mind you cannot have a fraction of an atom. You can't have half of an atom or a third of an atom. And that's what this slide is about. It's talking about the fact that you always have to have whole numbers of atoms and molecules. All right, first paragraph. In his atomic theory, John Dalton discussed how many atoms interact with each other when they form products. He wondered if whole atoms or fractions of atoms interact. Dalton concluded, and today we know, that elements combine in whole number ratios to form compounds, meaning that an entire atom of one element combines with the entire atom of another element when a compound is formed. This concept is called the law of multiple proportions. Compounds are not made up of, for example, half an atom of one element and a quarter of an atom of another. We use balanced chemical equations because we know that chemicals react with each other in small whole number ratios. So I added that to our notes. I included the title, Coefficients and Subscripts are always whole numbers in chemical reactions. And I just kind of rewrote that one paragraph a little bit. So I said the law of multiple proportions equals elements combine in whole number ratios to form compounds, meaning that an entire atom of one element combines with an entire atom of another element when a compound is formed. Compounds are not made up of, for example, half an atom of one element and a quarter of another. This is why we say there are two H2s instead of half an H2 or half of an oxygen atom. So here's our chemical equation we're using. We cannot split atoms unless it's a nuclear reaction like a bomb. Every formula is an example of the law of multiple proportions. Dalton said that atoms combine in whole number ratios to form compounds. On the basis of Dalton's discovery, you can look at the subscripts of chemical formulas and determine the ratio of atoms of each element in a compound. These are examples of the law of multiple proportions at work. So for example, if we look at H2O, how many H's are there? 2. How many oxygens are there? 1. These are examples of the law of multiple proportions at work. The point is that atoms combine in small whole number ratios with each other. Dalton made people aware that chemical reactions are not haphazard, randomized occurrences. In the early 1800s, when this was happening, this was quite a revelation to people who were beginning to sense the organizing principles of the natural world. So remember I said if you have H2O, you have 2 H's, 1 O. So let's look at some other examples. Our first example is KCl. How many K's do you have? Well, there's not a subscript here, so remember in math class, when we just have X, we know that it's 1X. Therefore, we would have 1K, and how many Cl's? 1. All right, so how many CAs are there? Again, no subscript, so we assume that there's 1. And how many chlorines are there? The subscript is 2. Therefore, there are 2 Cl's.
Mickey Mouse.
And it does look a little bit like Mickey Mouse. All right, so now, how many H's do we have?
1.
2, 3. And how many P's do we have? Just the 1. And what's the number by the oxygen? How many oxygens do we have?
1.
2, 3, 4. Yep, and so that's what our picture would look like. And our last one here, we have C12H22O11. So we have 12 carbons. We have how many hydrogens? 22. And how many oxygens? 11. So if you see, some molecules are really big, whereas others, like H2O, are really small. And that one looks a little bit like Pluto. And before you get too upset that my daughter's here, just so you know, this is a Sunday afternoon. So that's why I have my little helper here today. So I could get this ready for you for Monday morning. All right. So back to our notes then. So I said you can look at the subscripts of chemical formulas and determine the ratio of each element in a compound. So for example, if we look at water, there's 2 H's, 1 O, so the ratio of H to O is 2 to 1. Technically, you pronounce the colon as 2-TO, so it would be pronounced 2-to-1, but in common language, people kind of say "ta" instead, so it's like 2 to 1. All right, so our next section, we have atoms that look like turtles, yes. So balanced equations give you the ratios of reactants to products, but their actual amounts can be stated in different ways. The main focus of this unit is on figuring out how much of the reactants to use and how much product to expect. Balanced chemical equations show you only the ratio of reactants to products. So in these examples, we're going to talk about how many reactants we have compared to how many products in different. So the first way that we can compare our reactants to our products is how many atoms. So we can count up basically what they have here as the gray and the blue atoms that are represented by balls. So how many blue ones do we have on the left-hand side?
2.
Which we can also see because of the subscript 2. How many blue ones do we have on the right-hand side?
2.
Which we can see by the 2 that's distributed. How many little gray ones are there?
2.
And 2 over here, and 2 over here, which makes 6. Or in other words, distribute 3 times 2. And the same on the other side. 3 times 2 is 6. So the number of atoms of each element on the reactant side are going to equal the atoms of each element on the product side. But now we can look at the molecules. So even though there's 2 blue balls stuck together, there's stuck together into 1 molecule. And if we look here, there's 2 of the gray, 2, 2. But if I count up how many there are, there's 1, 2, 3 copies, and each one has 2 each. And if we look here, we got a 3 there. That's our coefficient. And so our coefficient tells us how many molecules of each there are. So there's 3 molecules of H2 and 1 molecule of N2 on the left-hand side. But if we look over here, there's how many turtle molecules? There's 2. And we can also tell that, of course, by drawing, but what's faster is looking at the coefficient, that there's 2 copies. Now this time the left side and the right side are not equal. There's 4 molecules on the left and 2 on the right, but that is okay because the number of atoms are the same on both sides. We can also talk about the mass. Now, each hydrogen weighs 1 AMU and each nitrogen weighs 14. So if I add the mass, 14 plus 14 is 28, 29, 30, 31, 32, 33, 34. That's the same on both sides. So the mass is going to be the same on the reactant and the product. And lastly, we can talk about the volume. So let's read the bottom. Volume at standard temperature and pressure. 1 volume of nitrogen, or in other words, 1 molecule, combines with 3 volumes, or 3 molecules of hydrogen, to make 2 volumes, or 2 molecules of ammonium. So the molecules and the volume, we use the coefficient. The mass, we use the periodic table to add up how heavy everything is. And the atoms, alright, and so I added that into our notes. Balanced equations give you the ratios of reactants to products, but their actual amounts can be stated in different ways. We can count the atoms, the molecules, the mass, or volume on each side of the equation. And then we have our review slide. Stoichiometry quantifies the amounts of reactants and products in chemical reactions. It's based upon the law of multiple proportions, meaning we have to use whole atoms or molecules. Balanced chemical equations describe the ratios of chemicals in chemical reactions. Quantities of reactants and products can be expressed in atoms, molecules, mass, or volume. All right, and that's the end of our lesson.